Hey, mathletes. What we're going to do in our last couple lessons is we're going to look at sequences and series, which we haven't seen in a while, have we? Since maybe 20-1. So let's see how this goes. They're actually what we do with them in calculus, or at least in Math 31, I shouldn't say in calculus in general, is not so bad, kind of easy. Okay, what we're going to only look at in calculus will be geometric sequences and series. So remember the term geometric means we're multiplying by something. And what we're multiplying by is known as the ratio. Okay, so let's do this. What we're going to do is we're going to look at infinite sequences that go on forever and ever and ever. How could we possibly find a limit for something that goes on forever and ever and ever? Well, let's find out. Look at the first one here. Sequence is 1, a half, a quarter, an eighth. So look at our numbers here. They're continually getting smaller and smaller and smaller. So what happens as the limit of this function, I'll call it n, goes to infinity of this function right here? What's going to happen? Well, this thing is going to approach 1/8, 1/16, 1/32, 1/64. It's going to approach something where we're going to get 1 over a really big, really big number. And 1 divided by a really big number is going to be 0. So the limit of this function will be 0. Okay, look at the next one. 2, 4, 8, 16. So it's doubling every time. So what would I say? What's the limit of this thing as it goes to infinity? Well, this thing is going to grow without bound. It'll never stop getting larger. So I'll say that the limit does not exist. And again, if you wanted to write, it's going to plus infinity for a sense of direction. Okay, so there's something really important, a difference between the two of these things, the first example and the second example, that we'll talk a little bit more in the next lesson. But what I want you to think about is for the first one, what is the value of the ratio? And what is the value of the ratio in the second one? And how will that help us determine if we can find the limit? Okay, we'll talk about that in the next lesson in series, okay? But for now, we'll leave it there. Let's look at a couple more basic examples. The limit as n goes to infinity of this. Well, we tackled something like this in the last lesson, okay? Where we've got a limit as n goes to infinity. So remember what we did was we divided by the highest power in the denominator. So when we do that, we're going to get 2 plus 3 over n plus 5 over n cubed over 1 plus 1 over n squared. And then as n goes to infinity, that'll go to 0, that'll go to 0, that'll go to 0. What do we have left with? Just 2 over 1, which is 2. Okay. On the next one, we do the same thing. So we divide by the highest power as n goes to infinity. Divide by the highest power in the denominator, I should say. Watch my words there. So I divide everything by the highest power. And as n goes to infinity, that'll go to 0, that'll go to 0, and we're simply left with then 0 over 3, which is 0. Okay? So again, just some limits as they go to infinity. Nothing too crazy there. Okay, here's some more sequences. So what this sequence would look like this is a sequence here. Like if I let n be 1, I would get 2/5. If I let n be 2, I'd get 4/25, and n be 3, 8 1/25, and so on and so forth. Okay, so these are sequences. We're just writing them as a function. Okay, what's going to happen here? Well, as n goes to infinity of this thing. Well, what's happening? Well, maybe I want to think of it like this. I'm going to rewrite this. I'm going to use my power law, and I'm going to rewrite it like that. So 2 to the n over 5 to the n. Now, if I sub in infinity, I'm going to get 2 to the infinity over 5 to the infinity, and that's a bit indeterminate, isn't it? So all I'm going to say to myself is, which one is going to grow faster, the numerator or the denominator? Well, the denominator is going to grow faster than the numerator. So this grows faster. So that means the bottom is going to get bigger faster than the top. And when the bottom is bigger than the top, as we go to infinity, we're going to get a value of 0. So when the bottom is growing faster, when the denominator is growing that much faster than the top, our limit will go to 0. Now, if you're like, oh, geez, that's kind of funky. Like, how do I know I got that right? Well, I just pick up a scientific calculator and I sub in some big numbers. And 100 is a big number, my friends. And you simply sub that into your calculator and you go 2 to the 100 divided by 5 to the 100. And when you stick that thing in your calculator, I already get 1.6 times 10 to the negative 40. Well, guess what? That's pretty much 0. So you can check your work here by picking up a scientific calculator. You're allowed to do that. Okay, one more of these crazy looking things. Limit as n goes to infinity of 2 to the exponent negative n. Okay, well, negative exponent, I don't like negative exponents. So let's rewrite this thing. That's 1 over 2 to the n, right? Write it with a positive exponent. Well, now, if we let n go to infinity, we're going to get 1 divided by a really big number. And 1 divided by a really big number, we know is 0. Okay? And again, you could check your work if you wanted to by subbing in a value like 100 or something and see what happens in your scientific calculator. Right? So today's lesson is very, very conceptual. I think the biggest piece of it is just thinking about what happens as n gets big. Will I go to positive infinity, negative infinity, 0? Maybe I'll go to a number. Okay, there's a short one on sequences. In the next lesson, we'll talk about series.